name is Willi Mickelson. I'm the Executive Director of CEIN, which is a nanoscience and nanoengineering center here on campus. And our goal is to enable applications of environmental monitoring using nanotechnology. And I'm sure you've all heard the word nanotechnology, but maybe some of you don't really know what the heck people are talking about when they say nanotechnology. So the first thing I'm going to do is just give an overview of what is nanotechnology. So if you're like me and you don't know something, the first thing you do is you go to Google and you type it in and try to figure out what it is. So if you type nanotechnology into Google, it shows that it's a branch of engineering that deals with things that are smaller than 100 nanometers. Okay, so it's something that's small. But what's a nanometer? We'll find out in a little bit. So nanotechnology, shortened to nanotech, is the study of the controlling of matter at the atomic and molecular scale. Okay, so it's on the atomic and molecular scale, and it's not just small things, it's controlling those small things. Another definition is nanotechnology is handling about 1 billionth of a meter, so that tells us what a nanometer is. At the molecular level, atoms and molecules are handled as individual components to create materials, small clusters of atoms, with unique characteristics. Okay, so another definition, if you go to nano.gov, real website, you'll get this definition. Nanotechnology is the understanding and control of matter at dimensions between approximately 1 and 100 nanometers, where unique phenomena enable novel applications. Okay, so what does that mean in regular English? So understanding and control of matter. So it's not nano by accident. You're actually trying to make nano things. Nanoparticles are all over the place. They've been around for millions of years, billions probably. But it's not just small things. It's controlling those small things. 1 to 100 nanometers. Okay, so it's really, really small. Unique phenomena. Okay, it's not just small, but it's small and different. And finally, it enables novel applications. So it's something new. It's not just all those things. It's also enabling novel applications. Okay, so nanotechnology timeline. When did this originate? So over 50 years ago, the famous physicist Richard Feynman said, it would be in principle possible for physicists to synthesize any chemical substance the chemist writes down. Give the orders to the physicist, give the orders, and the physicist synthesizes it. How? Put the atoms where the chemist says, and you make the substance. So this is sort of a new way of thinking to actually take individual atoms and construct something out of it, rather than having them just do it by their own natural processes. So then the first use of the word nanotechnology was in 1974, by Norio Taniguchi, where he was talking about production of very small nanometer-sized objects, which is common in today's computer industry. And then it became popularized by Eric Drexler when he wrote the book, Engines of Creation, The Coming Era of Nanotechnology. And one thing, probably the most popular part of that book was something called the gray goo. And as he said, the gray goo threat makes one thing perfectly clear: we cannot afford certain kinds of accidents. So what the gray goo was these nano box things that would self-replicate, and they self-replicated out of control and took over the world. So that's just a reminder that we don't want to go crazy with this nano stuff and try to do something that is not sustainable. So it's very important to be conscious about, just as with any science, to be conscious about what you're doing. Now, in 1989, scientists wrote IBM with xenon atoms on a nickel surface using a scanning tunneling microscope. So here's a little image right here, and what you see, each one of those dots is a xenon atom that's on a nickel surface. So here, 30 years after Feynman came up with this wild idea to move elements around, move atoms around, they actually did that with the scanning tunneling microscope at IBM. And then 12 years later, there was the Nanotechnology Initiative was created, and its goal was to advance world-class research and development programs, foster transfer of technologies for commercial and public benefit, develop and sustain resources and a skilled workforce, and then also, finally, support responsible development of nanotechnology. Okay, so how small is a nanometer? So here we have a chart, and on the left-hand side we have things that are natural, and on the right-hand side you have things that are man-made. So in the millimeter range, you have things like ants. So millimeters, pretty small, but you can see it pretty easily. And another thing is the head of a pin, again, small, and most people can see that. Now, when you get in the micron range, you start looking at things like dust mites, fly ash, the width of a human hair. And then on the things man-made side, you have things MEMS, micro-electromechanical systems. And these are things that are in your phones to say which way's up. They're in your cameras as well. They're also in your cars to say when you crashed, to deploy the airbag and things like that. So there's these little gears made about micrometers in size, so a millionth of a meter in size, and they're used in everyday technology. So again, another thing on the micron size is red blood cells. So that's at the micron scale, so 1/1,000,000th of a meter. So now you go down divide by another 1,000, you get into the nanometer range. And on the things naturally, you have DNA is only a few nanometers in diameter. You have enzymes, ATP synthase is an enzyme, and those are only a few nanometers in diameter. And also atoms, so actual atoms are only a tenth of a nanometer apart. And then on the things man-made side, you have a nanotube, other sorts of nano objects. The carbon nanotube is a sheet of graphite, or buckyballs. It's an atomic replica of a soccer ball, essentially. So this gives you an idea of what the scale is. If you're still looking for a little bit more what that means, so here's a scanning electron micrograph of carbon nanotubes and a human hair. And so a human hair, the width of a human hair is about 100,000 times bigger than a carbon nanotube. So what would that mean practically? So again, if you took a carbon nanotube and you were to expand it to make it 100,000 times bigger, you'd get something that looked like a human hair. And if you take the width of a human hair and multiply that by 100,000, you'd get about the size of a house. So what that means is that if you can imagine a carbon nanotube as a strand of hair, then a strand of hair would be as big as your house. So these things are extremely, extremely small. Okay, so what's different about nano? So it's small, but who cares? Why is it different? One of the things that's different is that because it's really small, you have things called quantum properties, which can dominate over bulk properties. So I'll give an example of that. So let's take a bulk semiconductor. It's a crystal of atoms laid out periodically in 3 dimensions. And if you were to look at what that thing looks like, it's pretty optically boring. It's usually pretty dark, gray or black. However, if you take a quantum dot, which is a small nanometer-sized crystal, and you're to look at its optical properties, it's very optically exciting. The fluorescence of these particles can depend on the size of the particles. So you don't just get one standard blah color. You can get any color you want by tailoring the size of these objects. So what's going on there? So if you take a bulk semiconductor and you shine light on it, say you had a laser or just any light, you excite something called an electron hole pair or an exciton. And this electron and hole will orbit each other just like planets orbit the sun, or just like electrons orbit an atom. And they'll have a characteristic radius of which they would like to orbit. Now when you get down into the nanometer regime, you have a quantum dot and you shine light on it, you'll still excite this electron hole pair. However, it has to live on that quantum dot. It can't just orbit any radius it wants. So it's confined to live on that quantum dot. And that squeezing of those excited electron hole pair makes it to where its energy, the energy of that excitation, depends on the diameter. So what happens is when these things recombine, you get light that emits. Light is emitted, and so what happens is that light that's emitted depends on the size. So you make the thing larger, it has a lower energy, and it's more red in color. If you make it smaller, it's more blue in color. So you can tailor the optical properties of your material by tailoring the size. Okay, so that's one thing that's different. What else is different? So the length scale are the same or even smaller than biological length scales. So what's an example of that? So here you have a gecko. If you've ever seen a gecko, it can climb up walls. It can even stand on the ceiling. And so if you look at the macro scale, you have a gecko or some sort of lizard. You look at the mesoscale, which means in between. You see its foot. You can see it has some sort of lamella on its feet there. And if you look on the micro scale, you can see that there's actually some fibers on there. And then you go down to the nanometer regime, you see that these things are only nanometers in diameter. And so the geckos use nanotechnology to climb the ceiling or stand on climb up the wall or stand on the ceiling. So here you see a scanning electron micrograph of a real gecko foot. You can see these long nanofibers with spatula tips. And researchers have been making synthetic gecko adhesive out of polymers using the exact same thing. This is done by Ron Fearing and others here at Berkeley. And so this is a way that we're actually using nanotechnology to mimic biology. Another example is using nanotechnology for targeted drug delivery. So here's a microsphere coated with nanowires. And these nanowires, if you tailor them to be the same size as these microvilli, which are these little hair-like particles that are all in your intestines and in your lungs, their interaction between these can be very strong. And so you can take So here's a scanning electron micrograph of this microsphere, and here's the microvilli. Now these things bind extremely strong to them. And so what you could use this for is targeted drug delivery. So you could put this in, a lot of times you take a pharmaceutical and 90% of it just goes right through your system. And this way you can tailor it to where it would bind to certain things and target that delivery. So you can either put in the inside this sphere or just embed it on the outside with the nanowires to have targeted drug delivery. Now this is in the research phase, no, this hasn't been commercialized yet. But this is the way you can target drug delivery. Another thing you could do is you could actually put certain proteins on those nanowires, and they'll have a certain binding affinity, so to bind to certain particular types of cells. Another example of nanotechnology with biology is here's some fluorescence images, and the red are fluorescent nanoparticles, much like I showed in the first part, and the green is a fluorescent dye, conventional ways of imaging biological materials. And the problem with the green dye is that, so here the green dye again is on the inside of the cell and the red is on the outside, and here it's the exact opposite on top. So the problem is that after only 3 minutes of exposure to the UV, you get bleaching and you've lost the fluorescent dye has lost its ability to fluoresce. And so if you use nanoparticles, they don't lose this they don't have this property of degrading over time, and so you can actually image for much longer periods of time and do studies where with conventional fluorescent dyes you can only do it for a matter of minutes. Another example is as I said, you can actually take a nanoparticle, here's a gold nanoparticle, and put a specific protein on there that binds to specific cells, and you can tailor those to bind to only cancer cells. And so if you were to take this nanoparticle and put a certain protein on there, it would bind to, say, only a certain type of cancer cell. And then you could take this and you could shine light on it, much like you would do normal radiation therapy. However, there'd be the gold nanoparticles would absorb the light much more, and you have the gold nanoparticles actually come inside the cell, these things called endosomes. And they would absorb this heat, they would boil the water, and the cell would then explode. And so you could use this to bind only to specific types of cells, the ones you want to destroy, and then have an increased effect on any sort of treatment you're going to do to that cell, rather than just irradiating the entire body. Okay, so that's another example. So a final example I'd like to show is the surface area to volume ratio becomes extremely large. So this is probably, I think, the most important of nanomaterials. So let's just look. So if you had a cube of length r, the surface area goes as the dimension squared, and the volume goes as the dimension cubed. So if you were to take the surface area and divide the surface area divided by the volume, you'd get r squared divided by r, or it would go as 1 over r. So that means that if you had smaller particles, you have a much larger surface area. So if you took a cube and then you were to break it into 10 little pieces, you'd actually get 10 times the surface area. And so this is important for a lot of different technologies, anything that has to do with surfaces. So catalysis is a surface reaction. Batteries, all those chemical reactions that drive electrical current in batteries are done on the surface. Filters, again, if you wanted to filter something, you want to have lots of surface area for things to bind on. Composites, if you wanted to integrate these nanomaterials with other polymers or other sorts of materials, the interface is all on the surface, and so you want to have something with a high surface area. And then again, sensors. Sensors. Sensors this is very important because if you're going to sense the environment or sense anything, everything interacts with its environment through the surface. So the larger surface area you have, the much more interaction you have with the surface. So here's an example. This is an anode of a standard battery. It has micron-sized particles. And then if you take an anode made from nanocrystals, you have a much higher surface area, and you can get much higher currents with the same volume or mass of your battery. And this is not just in the research phase. This is in commercial. This is commercialized. A123 Systems is a nanotechnology company, came out of MIT, and they have this the nanophosphate. So typically you have a phosphate microparticle, and the lithium ions have to interpolate in there for lithium-ion batteries. What they've done is they've found a way to stabilize very small, under 0.1 micron or 100 nanometer nanocrystals of these phosphate, and so you can get much faster interpolation into these nanocrystals, and much faster deinterpolation, so you can charge really fast and discharge really fast. And so here's the charging plot. So you charge to full capacity in a matter of 5 minutes. And these are not low power batteries. These things are being used So these large surface areas enable such large currents, depending on for the size that they are, and so you can get immense currents and very fast charging and discharging times compared to conventional batteries. Another area where the surface area makes different, and then this is sort of looking at biology, is you look at a lotus leaf. It has a property called superhydrophobicity. So what that means is that water droplets, they're repelled by it, but not only are they repelled by it, but they actually form almost a complete sphere. It's almost like they're levitating on top of this lotus leaf. And if you look at the nanoscale on the surface of this leaf, this is a computer-generated image. So you have, if you look at it, they have waxy bumps that are nanometers in size, nanometer in scale. And so what that does is it increases the surface area per projected area, projected area. And so what that means is that in order for the water to wet that, in order for it to spread out on it, it has to touch much more surface area than if it was just flat. And so that the water doesn't like wax, or water doesn't like oil, so it actually will beat up and actually levitate on top of the surface. And so this has been used for clothes. So you have clothes that have these nano-sized fibers on them, polymer fibers in them, and they actually they will not wet. And you can say, why don't you just wear a raincoat? Well, you could just wear a raincoat, but who wants to walk around with rubber on? You get the nice feel and breathability of cotton, but you pour water or whatever you want on it, and it just rolls right off. So an example of this is what you see here. Is this is a video of nanoglass. Let's see if this is going to work. So on the left-hand side, you have just a regular Petri dish, just normal glass. And on the right-hand side, you have nano-sized glass that's been put onto the surface of that. Okay, here we are. So you can see what they can do is drop water on here. If you drop water on the normal Petri dish, it just wets, it spreads around, not much happens. But when you drop it on the surface of the nanoglass, it beads up just like it does on lotus leaf. And it will not wet. And so, you know, you can use this for non-stick pans, or you can use this for a lot of other things. For wind turbines, for example, steam turbines, you don't want the water to sit there because it decreases your efficiency. So you put nano-sized materials on there, and it will not it will not wet it, and you'll be able to get much more efficiency out of your steam turbine. So you can see, it's almost like it's levitating, you know. It looks like water in space almost, because it is. It's actually almost completely removed from that surface, because the amount of surface area that it would have to cover in order to wet that surface is immense. Okay, so just to conclude, these are the three examples of what makes nanotechnology different. So what are potential nanotechnology applications? Medicine, again, there's diagnostics, drug delivery, energy, batteries, solar cells, fuel cells. For the environment, there's sensors, filtration, carbon sequestration. Again, it has large surface area, can absorb a lot of material per gram. Electronics, memory storage, thermal management, industrial, so composite materials, consumers, sunscreens, cosmetics, textiles, sporting goods. And so these are all the potential areas, and what I've highlighted here in red are things that actually have made it to the market already, and you'll be seeing these come into the market much more and more as time goes on. So just to conclude the first part of my talk, what is nanotechnology? Again, nanotechnology is understanding and control of matter at the dimension between 1 and 100 nanometers, where unique phenomena enable novel applications. So there's I highlighted three properties that make nanomaterials different. They're small, so their quantum properties can dominate. They are on the same or even smaller than biological length scales, which has interesting ramifications, and also they have extremely large surface area to volume ratio. So they're entering a wide range of markets. They'll bring great benefit, but we will have to sustain these things responsibly, develop them responsibly, make sure we don't contaminate the earth. There's a lot of worry about what potential adverse effects from nanotechnology could be. And people are working on making sure that that's not going to happen. Okay, so that's just sort of an introduction to what nanotechnology is in general. Now I'd like to get a little bit more into the research that we're doing at CEIN. And our goal is to enable environmental monitoring. So again, the mission is to inspire and realize applications directed toward monitoring environmental conditions. And there's three main applications we're going for. Personal environmental monitoring, something you can hold. Community-based environmental monitoring, this would be a fixed network, something on lampposts, on light posts, stoplights, that could give you a network, a map of what the environmental conditions Personal environmental monitoring, so there's pollution. Some people are very susceptible. People with asthma, for example, are very susceptible to environmental conditions. When the center started, they had this backpack technology where you'd have this very heavy backpack that had pumps and it was very loud, and it would sample and measure what the environmental pollutants were. There's been some advances here where these things can be handheld. They're still quite heavy and very expensive, but you can have a handheld device for one particular analyte. This is an example of a volatile organic compound sensor. And so our goal is to make these much smaller, lower cost, and something that people can easily use, and eventually something that will interface with cell phones and even be embedded inside cell phones. So for the community-based monitoring, here you see there's a natural gas explosion in San Bruno a couple years ago. That could have been prevented had there been an array of monitors. Also pesticides. Pesticides they put them on the crops, but a lot of times they drift away or they get built up in groundwater. So our goal is to, for example, put on these lampposts. Here's something that we've actually developed, a little sensing platform that can communicate wirelessly. It can measure sensors. It can interface with energy scavenging devices, and I'll get into all that later. So again, we want to enable fixed broad area coverage, and also semi-portable monitors for real-time feedback. A lot of times when people want to go measure something, they go to the field, they take a sample, they go to the lab, 2 weeks later they get the results, and they say, oh, you shouldn't be drinking your water. But realize you'd want to know that when you're drinking the water, not 2 weeks later. Or you shouldn't be breathing the air, you should stay inside, or so on and so forth. Okay, mobile environmental monitoring. There's a lot of examples where you don't want to send a person to go do something such as after an earthquake. Here's a picture from Haiti, or after a nuclear crisis where you have meltdown or on the verge of meltdown. You don't want to be walking people into there because it's very dangerous. Here, buildings can collapse. Here, you're going to get very high doses of radiation. And so there are sort of so-called deployable chemical detection systems. However, they're not very mobile. They're about the size of a refrigerator or a washing machine, and they can monitor toxic gases and things like that. So our goal is to take on the CEIN crawler to put sensors on there and have this thing be able to go into small areas, communicate wirelessly with rescue personnel or other devices or people, and have the ability to reach confined spaces. Okay, so just here's some block diagrams about how these things would be built. So you'd have a sensor that would, for example, measure pesticides or explosives or some toxic molecule, and then you'd have interface electronics to measure that, and then you'd have a power supply to power both of these two things. And then ideally you'd have something where everyone has a cell phone, and smartphones are going to be more and more prevalent. So it'd be a good idea to have something that can interface with the smartphone. Either plug into it and you just add your little personal monitor on there, or it would be something that would be sitting, say, in your room, and you would be able to just talk to it over the Wi-Fi or over Bluetooth. So community monitoring, again, you'd have a CEIN sensor that would detect something, and you have interface electronics. What would be different here is you'd have an energy harvester. These would be the personal monitor you can recharge every day, there'd be no problem, but these would like to be fixed and leave them there. So you'd have an energy harvesting apparatus, such as a solar cell or a vibrational scavenging device or a thermoelectric device. And then you'd be able to send this with a wireless remote and send them and be able to map them, much like you can look at Google Maps and then look at traffic. You could look at Google Maps and look at what the environmental conditions are. Okay, so mobile monitoring. Again, same sort of thing. You have sensors and interface electronics on there. However, you have a crawler. So you have the crawler has motors and actuators, has legs. It has these gecko adhesives that I mentioned earlier. These sort of polymer nanofibers to be able to climb all over the place. And then it has its own sort of onboard electronics to control the actuation of the legs and things like that. It has cameras and gyrometers and things like that. So in order to enable these applications, we have 5 areas of research with which we are engaged in. So they are energy, wireless, sensing, mobility, and electronics. And each one of these components is important to be in order to enable and realize these types of applications. So we have a broad base of faculty researchers. We're at 4 campuses. The bulk of us are here at Berkeley. We have a few people in Caltech, Stanford, and UC Merced. We have 10 represented departments and many faculty working on very applied research and also very basic research trying to understand the fundamental properties of these nanomaterials. So the first thrust, as we call it, I'll go into is the sensing thrust. So the goal is to develop state-of-the-art nanotechnology to enable these three applications. And two examples I'll give today are using phase display, which I'll tell you what that is, to create selective coatings, and then integrating these with ultra-sensitive nanoelectronic sensors. So like these sensors, again, the carbon nanotube or graphene, these nano devices have very high surface area, so they can be very sensitive to their environment. But you need a way to be selective. You want to know what you're sensing. So we've used this phase display to create very selective captures. And then also go into low-power microheated nanoparticle-based sensors. So conventional approaches for sensing a lot of times deal with polymers. You have a polymer, it has a certain monomer that then is linked together. And you have a single binding site. You have something here, and this is your target molecule. Say this is some toxic molecule that you would like to sense. It would bind to one of these things, but this one of these binding sites. However, they're all the same all over the place. So one approach is to take, instead of using conventional polymers, we use biopolymers, things called peptides, where they have amino acids that link to each other. And so you can tailor these things. There's 12 different types of amino acids. So you can tailor these things to where they have multiple binding sites. And so when you have multiple binding sites, you have the binding energy is higher, and so you get a much more selective binding to your analyte of interest. So how is that done? So that's done taking these bacteriophages, which are viruses that eat bacteria. And so what you do is you take with a random allotment. You can just take a random allotment of these bacteriophages, and you have these proteins displayed on the bottom, which are indicated here as these different shapes. And you have 10 to the 11 different types of these bacteriophages. And then you pan them over an analyte of interest, for example, TNT, an explosive, where you might want to sense that. And so what happens is certain ones of them will bind to it, and other ones will not. And so you wash away the ones that don't bind. You take the ones that do, you feed them some bacteria. They're very happy. They replicate. They have many more. And then you look at what these proteins are down there. Sorry, the peptide sequence down here, these amino acid sequence, and you look at them. And do they agree with each other? If they do, that's great. If not, do it again. Do it again and do it with harsher binding conditions. So make it a little bit harder for them to bind. And you do this a few times, and then when you get a consensus sequence, you get a peptide that has very specific binding to that analyte. So here's a molecule of TNT, and here's a peptide that was discovered that binds very specifically to that molecule. So if you look at the amino acid sequence, you see that. So there's 12 of them on this chain, and if you look at the one that they did for the TNT target, all of the top, the abundance from, so they did it for 4 rounds. So all the top 4 here all have this WHW, this tryptophan, histidine, tryptophan sequence right at the beginning, and that's what really binds very specifically to TNT. We've also done it for DNT, and there's less of a consensus among them. But you were able to get something that binds to TNT and does not bind to dinitrotoluene. So here's TNT, it has 1, 2, 3 nitro groups on it. Dinitrotoluene only has 2. So here's a measure of the binding affinity. And if you don't have any sort of specific, you just take the random allotment, you don't get very good binding at all. For the binding peptide that is tailored for dinitrotoluene, you get good binding for DNT and no binding for TNT. And the exact opposite for TNT, you get very good binding for extremely good binding for TNT and only moderate binding for dinitrotoluene. And so what we've done is we've taken this and we've taken these peptides and integrated them with a carbon nanotube transistor. So here's a cartoon image of 2 carbon nanotubes going between 2 electrical contacts, and you measure the current going through that. You apply a voltage and you measure the current going through that circuit as you expose it to different things. And what they've done is they've put a polymer on here, and on that polymer they've added this the peptide receptor on top of this polymer. And then if you expose it so this is the current going through that, if you start exposing it to TNT at very low concentrations, 1 femtomolar, the current starts to increase. So that shows that this thing is actually sensitive to TNT. But we don't want it just to be sensitive to TNT, we need it to be selective, because we want to know what we're detecting. So here is again the current going through this circuit here as they expose it to different concentrations. So you have 10 micromolar of toluene, which is the base molecule of this, very similar in structure, and there's no response whatsoever. Again, 10 micromolar of 4-nitrotoluene and 2-nitrotoluene, 2 different types of mononitrotoluene, and you get no response. 1 nanomolar of dinitrotoluene, and you get a little response. But then you go down to 1 femtomolar, which is 1 1/1,000,000th the concentration of a nanomolar, and you get this huge spike, showing that not only do we have something sensitive that can measure at the femtomolar level, we have something that is selective to TNT. Now this process of this phage display, process to make these peptides that are selective, has been done for other environmental toxicants. PBDE is a flame retardant that builds up in your body. We're working on getting sequences for that, and also pesticides. Here's alpha endosulfan and beta endosulfan. So we're looking at other peptide sequences that can be integrated with these carbon nanotube transistors to make selective sensors. Another type of sensor I can talk about is a nanoparticle-based sensor. So here, this is an example of a gas phase. The measurement there was a liquid phase measurement. This is a gas phase measurement. And so there's these things called microheaters, where you have this very thin membrane, and you can heat it up to very high temperatures at very low power because it's so thin, it's very small, so it doesn't have much thermal mass. And you can put nanoparticles on them, and you can make sensors using that. And here's an example, again, the current going through a circuit of this nanoparticle network. The blue line is a room temperature measurement done at 25 degrees Celsius, and it's actually been multiplied by 100. And this one is exposed to 50 parts per million of H2S. And you see there is some change in the current going through that at room temperature, but it's very slow to respond and very noisy, not very strong. The signal is not very strong. However, when you heat that up to 300 degrees, you get a very sharp response, and it plateaus, and you get a very large response and a very fast response. And so you can take these microheaters and put whatever sort of nanoparticle you want, depending on what you want to detect. This one was tailored for H2S, which is a toxic gas that's comes up from oil refiners and also very present in oil and natural gas reservoirs. And so you're able to heat this up at very low, only tens of milliwatts, and you're able to heat this up, so you can get a very low power sensor out of this using these materials. Now what we've done is we've taken this sensing platform, instead of just heating it continuously, which is already low power, we've actually heated it with very short pulses to even minimize the power even more. And so what you see here is a plot versus time of the conductance through the sensor. And on the bottom side here, you can see the hydrogen sulfide reference sensor. The dotted line is the target, and the solid line is the measured from a reference sensor. And you can see that when there's no H2S around, there's no response. And as soon as you expose it to H2S, the sensor responds. And we're able to get very good, very large, strong responses with very low power. So that those tens of milliwatts are now in the single milliwatts range because we're dealing in such a low duty cycle. And so we're enabling low power, so you don't have to scavenge as much energy from the environment, or your battery lasts longer, or however you want to look at it, and you're able to get good, strong signals from the analyte that you're trying to measure. Here's a plot up here of, again, more of that data of that heat pulsing, and this is the concentration of your hydrogen sulfide gas that you're delivering to it. And you can see as you increase the hydrogen sulfide concentration, the response of the sensor increases, and then when you bring the hydrogen concentration back down to zero, our sensor maps that reference sensor almost exactly. And so this is the response. If you look at the average response versus concentration, you get a good response curve here. So we're able to differentiate between, say, 200 ppm and 50 ppm. And here's the sort of error, the percentage error. At zero, there's a large percentage error because it's normalized by the signal. You have a small signal, you have a large fractional error. But here's the coin sensor, and we've got something that's always below 2%, and that's exactly the same, very similar to what we get for the photoluminescence detector, this $10,000 piece of equipment that uses kilowatts of power. And here we've got something that only uses milliwatts of power with comparable results. Again, on the selectivity side, you don't want just something to respond to everything. You don't know what you're sensing. So you need to make sure that you have something selective. So again, here are those heat pulses where you get measurements as you heat the sensor, and this is to 5 ppm H2S. Here we've exposed it to water, 13,000 parts per million, or about 40% relative humidity. And when you heat it, the conductance drops to zero. So that's the signal we're looking at. So we have no interference from water. And then for methane, there's no response whatsoever. And since H2S exists in natural gas reservoirs, methane is the main component of natural gas. So that's why we tested for that. And water is everywhere. You can't get away from water. And so we showed that we have good selectivity as well as sensitivity. Okay, so those are two examples of a liquid phase and a gas phase measurement of using nanomaterials and nano devices to measure in environmental conditions. So now I'll get into energy, our energy research. So we're doing research to be able to scavenge energy for these fixed devices. The community-based monitor, you want it to be able to scavenge energy from its environment so it can sustain power. Again, so we want to explore, understand, and develop nanotechnology-based energy scavenging and storage. We do some storage research as well to power these environmental monitoring applications. So I'll go into two different examples today. One is nanowire-based solar cells, and the other one is vibrational scavenging with piezoelectric polymers. So here, what you see, these three images are scanning electron micrograph images of silicon nanowires. So that you take a silicon wafer, you etch down in a controlled manner to create these nanowires, and you get these arrays of nanowires. And so so silicon is used for conventional solar cells, but here's an example of using nanotechnology. And why do we care about what do the nanowires offer? Well, one thing they offer is that due to the array of these nanowires, they actually trap the light very well. Silicon is a very poor absorber. Even though it makes the best solar cells, it doesn't absorb light very well. So you have to get a very thick piece of silicon if you want to make an efficient solar cell. And so what the researchers in CEIN have done is they've taken a nanowire solar cell and compared it to a planar solar cell, a typical solar cell. And so here is using only an 8 micron absorber, so the thickness beyond these nanowires is only 8 microns, and that's this blue line here. And that's comparable in efficiency, so this is the current versus voltage. What you want to see is you want to see a large current, so you want to be large down here, and then you want to see it extend a good amount into the positive voltage. So what they've been able to do is they've been able to get the similar efficiency with the 8 micron absorber compared to a 25 micron absorber. So you're able to use much less mass to scavenge the same amount of energy. So you get output powers around 5 to 6 milliwatt per centimeter squared, or efficiencies of about 5%, which is quite good for nanomaterials. So the nanowires act as a way to trap the light, so absorb the light much more efficiently in those solar cells. Another material we're looking at, silicon is a great material for solar cells, as I mentioned. It's very expensive to produce, though. Silicon is everywhere. It's in sand, but to extract very high purity silicon from the sand is very expensive. So a way to make solar cells on very cheaply would be a great advantage. So here we have a cadmium sulfide nanowire, and just using a solution process, we're able to exchange some of that cadmium with copper, and you're able to make this PN junction here, a radial PN junction, which is great for solar cells. You need a PN junction, and you have a very large interface here, which is what's again, the large surface area makes it advantageous for this application. Again, here's your cadmium sulfide nanowire. You take it, you replace part of it with copper sulfide using lithographic techniques, and then you wire it up. And these are SEM images, artificial color, but you have here's the PN junction, here's the core shell, copper sulfide with cadmium sulfide on the inside, and here is just the cadmium sulfide. And if you go and you shine light, and you raster your light beam over there, you can measure the photocurrent, and that's what this color here is. And so here is where you have the core shell, and you can see you get very high currents where you shine the light on that junction, showing that you have a good photocurrent and therefore a good photocell. And again, these efficiencies with these nanomaterials are about 5%. The top-of-the-line solar cells made from silicon are about 20% or so. So we're not there yet, but we're using much less material and potential to have a large impact. Another way that you can scavenge energy from your environment is through vibrational energy. So you have things vibrating all around. If you can extract that energy and convert it to electrical energy, that would be very advantageous. So here's an example of using polymer nanofibers, which are piezoelectric, which means that when you bend them, a voltage is generated on the ends. So you can take this polymer nanofiber, and you do it by a process called near field electrospinning, and you put it on any substrate you want. And you can put it on a flexible substrate. And this has been done by Li Lin in CEIN, and you can put these nanowires on these flexible substrates, and then when you bend those flexible substrates, they will generate voltage and scavenge energy. So again, as you start stretching, you have the increase in your current, and then you hold it, and it drops down, and then you release it, and the current goes the other way. So you can, if there's vibrations going on, you can take this flexible substrate that's moving around, to be able to turn some of that energy into electrical energy and use that for powering your sensors and electronics. Okay, so another one, again, for the mobile platform, obviously mobility is a big, you need to have a mobile device. So again, we're looking for a platform that can carry the coin sensors and has all-terrain mobility. I'll talk a little bit about the gecko-inspired nano-adhesives, and then also the Clash, the climbing autonomous sprawled hexapod. So here's that image again. And so the gecko here, and they have these nanofibers on them. And so, however, you don't just want nanofibers on there, you need to have some sort of hierarchical structure on there, because if you have a flat surface with some nanofibers on it, that works well for a very flat surface. But as soon as you start dealing with a bumpy surface, you're not touching all the surface that you want to. So if you embed some periodicity into that structure, it can conform to that surface and you get very good adhesion. And so we're looking at different ways of making hierarchical structures. Here's one where they actually just make slits in here. Also taking microfibers and putting nanofibers on top of them to deal with different roughness sizes. So here's Clash. It's a robot that runs on a DC motor, and it's very lightweight and very fast. It can run about a meter per second, and it's only about 10 grams, and it can climb up a lot of different surfaces. So here, you can either use a claw. So it has claws on its front feet, and it can climb up a cloth almost vertically, or you can click that one again. So, or if you put these gecko adhesives on here, it's a very smooth acrylic surface, and it's able to crawl right up that smooth surface by using these gecko-like adhesives. And so, using a combination of gecko-inspired adhesives and claws, much like a cockroach actually has claws and some fibers on it, and it can climb also to many interesting places. And so, you're able to be able to climb smooth surfaces and rough surfaces, such as here's the graduate student who developed this, Paul Bergmeyer, here's climbing up its couch. So here's some more footage of that.
Covering the Haiti earthquake for 5 straight days, and engineers at UC Berkeley are watching the events with keen interest.
This is after the Haiti earthquake.
Robot that can help rescue efforts in future earthquakes. Richard Bart shows us the drive to discover a safer way to enter collapsed structures.
This robot could one day assist in post-earthquake search and rescue.
The earthquake in 1989 actually is what inspired some of these small robots. And so you can send these robots into collapsed buildings, send them through very small holes trying to find people, and then having wireless technology relay that information back out to the top, signal where a survivor might be.
Cal grad student Paul Bergmeyer has already built nearly 100 of these with the help of Professor Ron Fearing and Kevin Peterson. Scavenging parts from cell phones and toys, they kept the cost to less than $1 each.
In very vast quantities, you think about making tens of thousands of them, because if you can save the rescuers from being in danger and find the survivors, having disposable robots is really worthwhile.
Tom Selleck's character battled similar creatures in a 1984 film that was pure science fiction. Today's is even better than the one in the movie. It incorporates a battery the size of a postage stamp, a camera from a cell phone, Wi-Fi from a custom Bluetooth circuit, and remote control from a toy bought at Radio Shack. The secret sauce is not the electronics, it's the structure to run like a cockroach, even climb obstacles, and the manufacturing process pioneered by Cal engineering students. Using a laser cutter, Bergmeyer can design and make a new robot in an hour out of cardboard. Cardboard so it can survive a fall from a 10-story building.
So you can throw it essentially from any height, it can hit concrete and survive and run away.
Run away at 5 feet per second via remote control. With the next step in robots, Richard Hart, ABC 7 News.
Okay, so another area that we do research is electronics and wireless. So we can measure those environmental monitors, whether it's on a personal or community-based, or on the mobile platform, which you just saw, and send that wirelessly out, and also do very efficient electronics, because electronics can actually consume a lot of power. So again, ultra-low power electronics for computation and storage, and also for wireless communication to enable these applications. So the one example I'm going to give today is a carbon nanotube radio. So in order to have a radio, you need 4 components, not including a speaker. So you need an antenna to receive the signal. You need to tune, so you need to filter out all the other stuff and get what you want. You need to amplify that signal, and then you need to a demodulator to extract the signal wave on top of the carrier wave. So it's sent on 101.3 FM, but the audio wave on that is much lower frequency. So you need to extract that lower frequency wave on top of the higher frequency wave. And it would be possible to construct this with nanomaterials. So you can take a carbon nanotube, it's very long and straight, it can be very many millimeters long, you could use that as an antenna. You can tune this, you can have this, this is a multi-wall carbon nanotube, and you can actually change the length and be able to tune what frequency it oscillates at. You can make amplifiers from carbon nanotubes, and you could also make diodes, which would act as a demodulator. But that's not, you don't need to do all those different things, you can actually do it with just one single carbon nanotube. And so what you have here is you have a carbon nanotube that's field emitting, meaning there's a large negative voltage applied to this electrode, and electrons are actually hopping off and flying to this positively charged electrode. And so the shape of this nanotube actually acts as the antenna, and the frequency, the natural frequency at which it will oscillate, gives it its tuning. And the amplification comes from the fact that you're in the field emission mode, so any sort of change in its geometry will drastically affect the field emission current. And then also, due to this nonlinearity of the oscillation, you get some demodulation from that. And so you're able to excite this carbon nanotube by exposing it to radio frequency. So here's when it's off resonance. You have a long, straight carbon nanotube, and it's field emitting, which you can see it's bright tip, so that's showing that it's field emitting. This is in the transmission electron microscope. And then when you tune into that frequency, you can actually see that this thing is vibrating all over the place. You can see the base is fairly stable, but you can kind of see its terminal points here. It's a little bit hard so you can see it's just vibrating there. So you can take this thing and you can excite it with radio frequency, just like you would a regular radio, and you can actually use it as a radio receiver. So they're tuning the frequency to reach the intrinsic frequency of the carbon nanotube. And once it's on resonance, you can see it's got all blurry because it's moving, it's doing its amplification, and it's receiving that signal, so you can't see it. A little bit static, but that can be filtered from electronics. This is the raw data coming out of there. And then it's been detuned, the carrier frequency, they change the channel. We're not listening to the ley line anymore, and so the thing doesn't vibrate anymore. So that's an example of using nanotechnology for novel wireless applications. So in addition to doing the research in each of those 5 categories, we're also integrating all those different things. We're taking sensors and electronics and energy scavengers and building systems around those. So as I showed earlier, there's this, we've made this coin sensing system that can house a sensor. It can measure multiple types of sensors, any sort of sensor you want to measure electronically, either the nanoparticle sensor, the carbon nanotube peptide sensor, or a graphene sensor, or any sort of electronic sensor you want to give us. We would be able to mount it on here and be able to measure it. It can also do heater control if it needs to heat the devices at all, for example, for that nanoparticle sensor. It has an onboard CPU, a microprocessor. It has a radio that's compliant with this IEEE 802.15.4, and it has wired USB communication links. It also has energy scavenging capabilities and can charge batteries. And so we've taken this coin sensing system, as we call it, and we've mounted different types of sensors on there. And we can the idea is to take this sensing system and mount it on top of the crawler, or have it be a standalone system. And since it has wireless communication, it can actually communicate through a wireless access point, so you can have an access point and then send that data out to wherever you want it in the world. You just have to log into this server, and you'd be able to stream data. Here you can see this is actual data from a sensor, an ammonia sensor. So this is was water on here, and they dropped ammonium hydroxide on there, and it drastically changed the current, so you're able to monitor, get that data over the wireless link. Now, most recently, we've actually taken the server out of the mix, and we're able to take communicate directly from the iPhone to the sensing system itself. So you could have these things in a room. You could go in there with your smartphone. You could open up your coins application. You say what's the situation? What's the environmental conditions? And it can send that information back. We've also so we can take this thing and we can mount it on the crawler, or we could also use that thing again as a fixed station that we would then interrogate with something else. So you could have these things. If these things were all over the place, you could send in your crawler. You could go ask for what the environmental conditions are, and then do something with that information. And so what we've done here is we've mounted this. So here is our coin sensing system, and here's one of those crawlers. This one's actually made out of balsa wood. So and we've mounted a humidity sensor on there, a coins generated humidity sensor. And so what you'll see is you come over to it. So now these things are right next to each other, but they could be across the room. We just don't have the camera to show that. So we breathed on it. It's thinking, it sends a signal, it says go run. But it could send anything. It could say, stop, go back. It could say, go tell the rescuers there's somebody here. So you can mount any sort of sensor you wanted on there, and it would be able to communicate between those two things. So those are sort of the ways that we're taking the sensors and being able to communicate that information wirelessly, so that you can actually do something useful with that information. And so with that, if someone's, oops, let's see here. That someone just dinged me at 1 o'clock. So that's I'd like to conclude with that. We're doing research in all these different areas: mobility, sensing, energy scavenging, electronics, and wireless. And we're trying to integrate all those things into one system to enable personal, community-based, and environmental monitoring. And with that, I can take any questions anyone has.
How stable and reusable are ideally when they get commercialized, these sensors, they can detect organic substances?
Sure, that's a great question, and I'm not sure what the carbon nanotube-based and peptide ones. I'm not sure how stable those are, because those are typically done in short term. But I'm involved with the nanoparticle research, and we've looked over 3 months. So we've tested them, combined, put them on the shelf, test them some more, put them on the shelf some more, and put them back. So 3 months, they seem to be stable.
They didn't degrade.
They didn't degrade over that time frame. Of course, for some of these applications, you want them to last for a year, so that's still to be determined. But for the liquid-based one, that's more of the sort of go and measure. You would go to a field and measure something, because again, a lot of times they take a sample and bring it back to the lab. That one's tailored towards going towards your well, dipping in the well. Do I have any pesticides in my well? Do I have any this in my well? And so you could have that on a very cheap, reusable or disposable sensing component, have a reader that would plug in. Yeah.
For the gas sensors of hydrogen sulfide, are there any limitations to the molecule that could be sensed? Carbon monoxide?
Carbon monoxide would definitely be able to, in fact, there's very good carbon monoxide sensors out there, so we're not really developing that. You plug into your wall, they last for quite some time. But no, if you wanted to, that is the materials we're using nanomaterials, but the base material is semiconductor metal oxide. It's actually tin oxide that's in those carbon monoxide sensors, and that's what measures, that's what detects carbon monoxide. You could make one of these and have it be lower power than the conventional ones, or be faster responding or something like that for carbon monoxide. But we're looking at other analytes of interest. That would be one. Hydrogen sulfide is one. Ozone is another one, because that's in the Central Valley there's lots of ozone from diesel trucks and things like that. So it'd be good to know whether it's safe to go running that day or whether you should wait till some other time and not expose your lungs to those chemicals. Yeah.
You seem to emphasize with solar panels the decrease in the amount of material and weight, but it seems like efficiency would be a potential area to reduce a lot of the surface area.
Absolutely, that's absolutely true. For installing, for when you look at the cost of solar cells, the cost of installation is also comparable to the manufacturing cost of the cell. So that's definitely something to be sort of, because you need the efficiency. It's really what you care about is your dollars per watt installed. And so we're not there yet. We're not there yet with the nanomaterials. But if you look at when solar cells first started, I don't think you were looking at 20% efficiency. That's when you really get processing down and things find a way to fabricate these with very, very well-controlled processing, we might be able to eventually beat them or enhance conventional electronics, conventional solar cells. In addition to the data that I showed today, and the project that I showed, we're looking at using silver nanoparticles on top of conventional solar cells because, as I said, it's a bad absorber. But those silver nanoparticles actually enhance the local fields and scattering it, so you get much more absorption of your conventional solar cell by putting something that increases the light absorption efficiency. So you're absolutely right. We're not there. It's really the efficiency that gets there, but that doesn't mean that, since we're not there yet, doesn't mean we shouldn't be trying. Yeah.
The claw robots are incredibly awesome. Are you planning to use them the next time there's some sort of birthday?
So we could use them. We don't have plans to do that. That is the eventual goal. We don't manufacture them. You saw the graduate student. He's the one that's doing it. In order for it to be effective, we need to be mass producing these things. But we're not there yet. But that's what we'd like to enable. So maybe in a couple of years, you'd like to start a company, and we could show you how to do it. Yeah.
We're going to see them scurrying around airports and saving us from taking off half our clothes when we go through security.
Hopefully. That's a potential one. Airports, it might be, but airports that have, they have wall control, you can walk through them. So you'd be able to put sensors that wouldn't need mobility. However, one thing that would be useful is port security. So you can put, another thing again that I didn't mention here, just due to the lack of time, is looking at some ways to detect radiation. Mount a radiation detector on them and have it run through shipping containers and see if there's any fissile material, any sort of nuclear bomb or anything like that, which is a big, there's a big thing, and you use helium-3 now for those detectors, and we're running out of helium-3, and so we're going to need another solution to that. So that would be one thing, sort of port security. I'm not sure if airports would really be seeing some of these other things, the sort of fixed monitors, sure, you could see those. Yeah?
A couple of years ago, the micro cantilever sensors were a big thing. Do you see this supplanting many of those applications?
Yeah, so we did look at some of the micro cantilever, the piezo-resistive micro cantilevers. So yeah, these could definitely, we've sort of left those behind in favor of some of these other nanoelectronic ones. So I do think that these could supplant some
I was thinking in terms of mercury sensing, vapor and liquid mercury.
Yeah, so we are looking at other ways to sense mercury electrochemically and things like that. The data that I shared on the peptides, those are more tailored for the individual, the medium-sized molecules that you can't, if you talk about a single atom, mercury, you can't really tailor multiple binding sites for a single atom. There's going to be one binding site for that particular application. So that's more for the organic molecules and things like that. But there's definitely, some electrochemical, these carbon nanotubes can be used for electrochemical electrodes, and I know that sensing mercury with electrochemistry, there's a lot of research going on in that area. Yeah.
So that would also possibly be the next step from MEMS down to
Now, absolutely, yeah. So one thing I didn't share here was they made, using a carbon nanotube, maybe it was 5 or 6 years ago, they were using a multi-wall carbon nanotube to actually remove the outer walls, and they put a rotor on the outer wall of the center part, and they were actually able to make that rotor move around, so it actually were able to make a nanometer size motor.
I was thinking more in terms of replacing the accelerometers.
Sure,
Which
sure.
are, now state of the art now is a very sensitive MEMS accelerometer.
Yeah,
Stated yet smaller.
absolutely. So for that, they're already pretty small. So if you need the smaller one, you could make a smaller one. It gets a little bit, the smaller and smaller it gets, the more difficult it gets to make things. So they work pretty darn well now. If you needed something, if you had a, you had a little fly that was moving around or something, nanomechanical fly, then maybe you'd want a milli or micro, size fly that was flying around. Then yes, a nanometer size accelerometer would be very useful. Yeah, but they could be, you never know where it's going to go.
You thought of doing any kind of biological interface kind of thing where you might take a fly and stick a sensor on it, have it buzz around the room?
We aren't doing things like that, but I've seen pictures of cockroaches with wires coming out of their head and things like that. And when you're talking about flying in particular, it's really hard to beat nature. And so before you see any sort of nanomechanical fly flying around, you probably see a fly with some LEDs on its head people are doing research into making glucose monitors and also other biological, disease markers and things like that.
Marker like airborne,
Oh.
H1N1, flames, color vibrant.
Yeah, so these the sort of readout mechanisms of the carbon nanotube transistors could be very useful, or the other nanoelectronics. But it's really on the biology side of H1N1 is going to have those specific proteins on there. So you could take, just like we put the peptides on these carbon nanotubes, you could take those specific proteins or whatever it is that are displayed on the H1N1 or other sorts of biological, E. coli or something like that, or Giardia or something like that. You can take those and put those on there, and you should be able to read them out in the same manner. Yeah, in the back there.
Is there any questions?
Okay, thank you. You have a quantum dot and you shine light on it, you'll still excite this electron hole pair. However, it has to live on that quantum dot. It can't just orbit any radius it wants, so it's confined to live on that quantum dot. And that squeezing of those excited electron hole pair makes it to where its energy, the energy of that excitation, depends on the diameter. So what happens is when these things recombine, you get light that emits. Light is emitted, and so what happens is that light that's emitted depends on the size. So you make the thing larger, it has a lower energy, and it's more red in color. If you make it smaller, it's more blue in color. So you can tailor the optical properties of your material by tailoring the size. Okay, so that's one thing that's different. What else is different? So the length scale are the same or even smaller than biological length scales. So what's an example of that? So here you have a gecko. Have you ever seen a gecko? It can climb up walls. It can even stand on the ceiling. And so if you look at the macro scale, you have a gecko or some sort of lizard. You look at the mesoscale, which means in between. You see its foot. You can see it has some sort of lamella on its feet there. And if you look on the micro scale, you can see that there's actually some fibers on there. And then you go down to the nanometers, and you see that these things are only nanometers in diameter. And so the geckos use nanotechnology to climb the ceiling or stand on climb up the wall or stand on the ceiling. So here you see a scanning electron micrograph of a real gecko foot. And you can see these long nanofibers with spatula tips. And researchers have been making synthetic gecko adhesive out of polymers using the exact same thing. This is done by Ron Fearing and others here at Berkeley. And so this is a way that we're actually using nanotechnology to mimic biology. Another example is using nanotechnology for targeted drug delivery. So here's a microsphere coated with nanowires. And these nanowires, if you tailor them to be the same size as the... My name is Willi Mickelson. I'm the executive director of CEIN, which is a nanoscience and nanoengineering center here on campus. And our goal is to enable applications of environmental monitoring using nanotechnology. And I'm sure you've all heard the word nanotechnology, but maybe some of you don't really know what the heck people are talking about when they say nanotechnology. So the first thing I'm going to do is just give an overview of what is nanotechnology. So if you're like me and you don't know something, the first thing you do is you go to Google and you type it in and try to figure out what it is. So if you type nanotechnology into Google, it shows that it's a branch of engineering that deals with things that are smaller than 100 nanometers. Okay, so it's something that's small. But what's a nanometer? We'll find out in a little bit. So nanotechnology, shortened to nanotech, is the study of the controlling of matter at the atomic and molecular scale. Okay, so it's on the atomic and molecular scale, and it's not just small things, it's controlling those small things. Another definition is nanotechnology is handling about 1 billionth of a meter, so that tells us what a nanometer is. At the molecular level, atoms and molecules are handled as individual components to create materials, small clusters of atoms, with unique characteristics. Okay, so another definition, if you go to nano.gov, real website, you'll get this definition. Nanotechnology is the understanding control of matter at dimensions between approximately 1 and 100 nanometers, where unique phenomena enable novel applications. Okay, so what does that mean in regular English? So understanding and control of matter. So it's not nano by accident. You're actually trying to make nano things. Nanoparticles are all over the place. They've been around for millions of years, billions probably. But it's not just small things. It's controlling those small things. 1 from 100 nanometers. Okay, so it's really, really small. Unique phenomenon. Okay, it's not just small, but it's small and different. And finally, it enables novel applications, so it's something new. It's not just all those things, it's also enabling novel applications. Okay, so nanotechnology timeline. When did this originate? So, over 50 years ago, the famous physicist Richard Feynman said, it would be in principle possible for physicists to synthesize any chemical substance the chemist writes down. Give the orders to the physicist, give the orders, and the physicist synthesizes it. How? Put the atoms where the chemist says, and you make the substance. So this is sort of a new way of thinking to actually take individual atoms and construct something out of it, rather than having them just do it by their own natural processes. So then the first use of the word nanotechnology was in 1974 by Norio Taniguchi, where he was talking about production of very small nanometer-sized objects, which is common in today's computer industry. And then it became popularized by Eric Drexler when he wrote the book, Engines of Creation, The Coming Era of Nanotechnology. And one thing, probably the most popular part of that book was something called the gray goo. And as he said, the gray goo threat makes one thing perfectly clear: we cannot afford certain kinds of accidents. So what the gray goo was these nano box things that would self-replicate, and they self-replicated out of control and took over the world. So that's just a reminder that we don't want to go crazy with this nano stuff and try to do something that is not sustainable. So it's very important to be conscious about, just as with any science, to be conscious about what you're doing. Now, in 1989, scientists wrote IBM with xenon atoms on a nickel surface using a scanning tunneling microscope. So here's a little image right here, and what you see, each one of those dots is a xenon atom that's on a nickel surface. So here, 30 years after Feynman came up with this wild idea to move elements around, move atoms around, they have an idea of what the scale is. If you're still looking for a little bit more what that means, so here's a scanning electron micrograph of carbon nanotubes and a human hair. And so human hair, the width of a human hair is about 100,000 times bigger than a carbon nanotube. So what would that mean practically? So again, if you took a carbon nanotube and you were to expand it to make it 100,000 times bigger, you'd get something that looked like a human hair. And if you take the width of a human hair and multiply that by 100,000, you'd get about the size of a house. So what that means is that if you can imagine a carbon nanotube as a strand of hair, then a strand of hair would be as big as your house. So these things are extremely, extremely small. Okay, so what's different about nano? So it's small, but who cares? Why is it different? One of the things that's different is that because it's really small, you have things called quantum properties, which can dominate over bulk properties. So I'll give an example of that. So let's take a bulk semiconductor. It's a crystal of atoms laid out periodically in 3 dimensions. And if you were to look at what that thing looks like, it's pretty optically boring. It's usually pretty dark, gray or black. However, if you take a quantum dot, which is a small nanometer-sized crystal, and you're to look at its optical properties, it's very optically exciting. The fluorescence of these particles can depend on the size of the particles. So you don't just get one standard blah color. You can get any color you want by tailoring the size of these objects. So what's going on there? So if you take a bulk semiconductor and you shine light on it, say you had a laser or just any light, you excite something called an electron hole pair, or an exciton. And this electron and hole will orbit each other just like planets orbit the sun, or just like electrons orbit an atom. And they'll have a characteristic radius of which they would like to orbit. Now when you get down into the nanometer regime, actually did that with the scanning tunneling microscope at IBM. And then 12 years later, there was the Nanotechnology Initiative was created, and it was its goal was to advance world-class research and development programs, foster transfer of technologies for commercial and public benefit, develop and sustain resources and a skilled workforce, and then also finally support responsible development of nanotechnology. Okay, so how small is a nanometer? So here we have a chart, and on the left-hand side we have things that are natural, and on the right-hand side you have things that are man-made. So in the millimeter range, you have things like ants. So millimeters, pretty small, but you can see it pretty easily. And another thing is the head of a pin, again, small, and most people can see that. Now, when you get in the micron range, you start looking at things like dust mites, fly ash, the width of a human hair. And then on the things man-made side, you have things MEMS, micro electromechanical systems. And these are things that are in your phones to say which way's up. They're in your cameras as well. They're also in your cars to say when you crashed, to deploy the airbag and things like that. So there's these little gears, mean about micrometers in size, so a millionth of a meter in size, and they're used in everyday technology. So again, another thing on the micron size is red blood cells. So that's at the micron scale, so 1 millionth of a meter. So now you go down divide by another 1,000, you get into the nanometer range. And on the things naturally, you have DNA is only a few nanometers in diameter. You have enzymes, ATP synthase is an enzyme, and those are only a few nanometers in diameter. And also atoms. So actual atoms are only a tenth of a nanometer apart. And then on the things man-made side, you have a nanotube, other sorts of nano objects. The carbon nanotube is a sheet of graphite, or buckyballs. It's an atomic replica of a soccer ball, essentially. So this gives